This is the final submission video for the ISEC Space Elevator Challenge 2023. Hello everyone, my name is Kuzuno from Japan, and I am going to speak about our mission, high-level nuclear waste disposal system using space elevator. I will introduce the background. In today's world, there is a growing demand for sustainable energy resources to achieve a greener Earth. Nuclear energy would be a promising candidate due to its high energy generating capacity. However, the disposal of nuclear waste remains a significant challenge. Specifically, the disposal of high-level nuclear wastes, or HLWs, poses a critical issue due to their high levels of radiation. Currently, there are approximately 20,000 HLWs on Earth, posing a long-term threat to our environment. Therefore, it is crucial to develop disposal methods that ensure long-term safety for HLWs. Several ideas have been proposed for the disposal of HLW, including options like sea or ice disposal, indoor management, and geological disposal. However, these ideas come with certain drawbacks, such as treaty obligations or high management costs. As a result, none of the current approaches seem promising when it comes to ensuring permanent safety for human habitation. Compared to disposal on Earth, space disposal offers a promising solution due to its long-term safety and cost-effectiveness. Research on nuclear space disposal was initiated by NASA in the 1970s and 1980s, with the space shuttle considered as a potential means of transportation. However, this idea was eventually abandoned due to concerns over the technical reliability of rockets and the overall cost efficiency. In contrast to that, a space elevator is expected as a low-cost and safe space transportation system in the future. This is why we focused on nuclear waste disposal using space elevators. Let me outline our mission objectives. Our primary goal is to assess the feasibility and efficiency of employing a space elevator for the disposal of high-level nuclear waste. Previous research conducted by Hein has explored the use of space elevators for nuclear waste disposal, which serves as the foundation for our work. Building upon Hein's research, we have introduced additional technical insights and conceptual updates to further enhance the mission's potential. Furthermore, we will compare the cost efficiency of the space elevator approach with other space transportation methods. I will now outline the mission flow. First of all, nuclear waste generated at nuclear plants undergoes processing to make it suitable for space disposal. Once the high-level nuclear wastes, HLWs, are processed, they are transported to the anchor point of the space elevator. Once the climate reaches a specific altitude, the HLW canisters are separated. Canisters can reach beyond the GEO without the need for propellants due to the characteristics of the space elevator. We propose the unmanned climbers in the mission to ensure operational safety and improve the mass ratio of the HLWs. In this mission, we consider vitrified HLW as a payload due to its chemical stability and durability for corrosion. Previous studies designed to cover the payload with a spherical shield as shown in the left figure. And we suggest equipping radioisotope thermoelectric generator or RTGs and beacon. By equipping RTGs and utilizing the heat of HLW, additional climber power source can be expected. And we adopt spring-type payload attachment fitting when separating the HLW payload and climber. A spring-type path separates by using the storing energy of the clamp band. It will realize softer separation than the separation by pipe techniques. Next, I will discuss the disposal destination of HLWs. there are several candidates for final destination of nuclear waste. Isolation from the biosphere would be a top priority, but it requires comprehensive assessment of multiple factors to determine the most suitable orbit. We conducted a rough evaluation of each candidate in terms of safety, cost, and potential drawbacks, as shown in the table. One of the candidates, escape orbit from solar system, can achieve the permanent isolation, and therefore it will be the most promising option in terms of safety. However, it requires huge delta V for orbit transition. The specific value is around 42 km per second. We investigated how much this additional delta V can ease by using space elevator. Required escape velocity from solar orbit at tether edge can be obtained from the law of energy conservation shown in the middle. Finally, required delta V would be 4.3 km per second. That would be a more realistic figure. Therefore, we can suggest that the feasibility of solar escape orbit option will be enhanced by using the space elevator. We newly suggest the use of non-vectorial space elevator in this slide. Nowadays, the number of spacecraft or space debris is increasing in the GEO. Therefore, we propose using a non-vectorial space elevator for avoiding the collision between the tether and the spacecraft in GEO, as shown in the left figure. But the release point of the payload would differ from that of the normal equatorial space elevator. So we conducted orbital analysis to confirm whether the orbital propagation is stable. We accounted for solar radiation and J2 gravitational term as disturbances. And here is a comparison of the orbital radius history of the objects thrown by equatorial and non-equatorial space elevators. As a result, there were no changes in orbital radius. Therefore, we found that both concepts of equatorial and non-equatorial space elevator can be used for the mission. Next, we conducted heat analysis to confirm whether the system can endure the heat generation of HLW. We considered two main heat sources, sun radiation and HLW. The most critical thermal situation for the space elevator is when it inclines 23 degrees. Sun radiation is fixed in this situation. We assume a tapered carbon nanotube tether in this mission. We newly introduced the thermal formulation for tapered tether as shown in the left side. The tapered function of the tether was referred to the Pearson's formulation. Right figure showed the result. The heat generated from HLW depends on its amount. We consider three cases of the HLW amount. The result indicates the heat generated from HLW did not have a significant impact on the space elevator compared to that of sun radiation. Finally, we compared the efficiency of this concept in terms of cost and operation time. This diagram compares the required operation time and cost to dispose of all of the existing HLW by using four transportation means. Considering that the amount of HLW would increase in the future, it is desirable to have a shorter disposal period. As shown in the diagram, space elevator has the lowest cost and the shortest year for disposing of currently existing HLW, even though its final destination is the farthest among the four candidates. Therefore, we can say that the space elevator would be the most cost and time-effective approach. I will conclude our topic. We investigated the feasibility and effectiveness of the space elevator for HLW disposal missions. Specifically, we had three contributions to that idea. First, we provided some concept level updates. Second, we performed some updated analyses such as thermal and orbital ones, and we showed some novelties. Third, we compared cost efficiency among several approaches, and we concluded that the space elevator can be the most promising approach from the viewpoint of cost and mission time. Thank you for listening.